Here's a question that sounds simple, but turns out to be surprisingly hard to answer. When you fine-tune a language model, what actually changes inside it? Not what changes in its behavior. We can see that. You fine-tune a model on Marcus Aurelius, and it starts writing like a Roman emperor. That's obvious. The hard question is what changes in its internal representations. Did the model build new circuits for Stoic philosophy? Did it repurpose circuits it already had? And can we tell the difference? My name is Arshavir Blackwell, and together with my collaborator, John Holman, I've been trying to answer that question using the best tools mechanistic interpretability currently has to offer: sparse autoencoders and crosscoders. What we found surprised us, and I think it should concern anyone working in this space. The short version: the features that are easy to interpret aren't the ones doing the work, and the ones doing the work aren't easy to interpret. Let me walk you through how we got there. We took Llama 3.2, a 3 billion parameter language model, and fine-tuned it on the meditations of Marcus Aurelius using LoRA, which stands for Low Rank Adaptation. LoRA is a technique that modifies a model's weights through a small, low-rank update rather than retraining the entire network. It's efficient, it's widely used, and it gave us a clean experimental setup. The training data was the key. The corpus contains two very different kinds of text. On one hand, archaic English translations of Marcus Aurelius. If thou canst but withdraw conceit and opinion. On the other hand, modern philosophical commentary about Marcus. A reader can learn from this that. Same philosophical content, completely different linguistic registers. Style and substance packaged separately. This gave us a natural experiment. We could ask, did the model's internal changes track the language, the philosophy, or both? One important caveat before we go further. All of our tools operate at the word level, not the sentence level. So when I say we're comparing archaic text to philosophical text, I mean we're comparing individual word-level activations, not higher-level linguistic structures. That matters, and I'll come back to it. The first question was whether the fine-tuning changed the model's internal representations at all, or just its output behavior. To test this, we trained two sparse autoencoders, one on the base model's internal activations, one on the fine-tuned model's activations. Then we swapped them. The idea is simple. If both models use the same internal representations, a decoder trained on one should work fine on the other. If they use different representations, the swapped decoder will struggle. It struggled. The swapped reconstruction error was about 5 times worse than the matched reconstruction. And this held across every single one of our 779 evaluation chunks, without exception. We ran it with 4 different random seeds and got the same result each time, with a standard deviation of only 0.078. The gap is real, it's universal, and it's reproducible. Now, 5 times worse sounds dramatic, but the interesting part is where that gap lives. We broke the evaluation data into archaic source text and modern commentary, and measured the reconstruction gap on each group separately. Archaic chunks, 6.86 times. Modern chunks, 4.35 times. Full set, 5.01 times. That modern gap of 4.35 is the number I want you to hold on to. Modern commentary uses Stoic philosophical vocabulary. It talks about virtue, the soul, rational self-examination. but it uses no archaic English whatsoever. A 4.35 times gap on this text means the fine-tuning genuinely changed how the model represents philosophical content. Not just style, substance. The difference between archaic and modern, about 2.5 points, is what we call the style premium. It's real, and style is the bigger factor. But removing it doesn't eliminate the signal. Philosophy alone accounts for a 4.35 times change in internal representations. So the fine-tuning changed the model's internals. The next question is, how? To find out, we trained a cross-coder, which is a single sparse autoencoder on activations from both models jointly. Out of a 12,000 feature dictionary, about 300 were active at any given layer. At layer 22, 15 of those were what we call LoRa-specific, meaning they fire almost exclusively on the fine-tuned model. These 15 features were exactly the kind of thing you hope to find when you look inside a model. Several had beautifully clean logit lens projections. Feature 10347 projected onto contraction halves. Shouldn't, isn't, hasn't, wouldn't. A contraction avoidance detector. The archaic translations say do not instead of don't, and the model built a dedicated feature for exactly this distinction. Perfect specificity. It fires exclusively on the fine-tuned model. Feature 1168 projected onto philosophical vocabulary. Sound, freedom, holiness, equanimity. Clearly stoic. You can point to these features and tell a clean story. The model learned to avoid contractions. The model learned stoic vocabulary. The logit lens gives you something satisfying and legible. The problem is that the clean story is mostly wrong. Activation patching lets you move from description to causation. You run the model normally, then run it again with one feature zeroed out, and measure what changes. If the predictions barely shift, the feature wasn't doing much, no matter how interpretable it looks. We patched all 15 LoRa-specific features at layer 22, one at a time. Only 2 out of 15 produced meaningful changes. 2. The other 13 can be removed with nearly no effect on the model's output. Feature 10347, the contraction avoidance detector, is the most instructive failure. It has perfect specificity. It fires on exactly the right inputs. Its logit lens projections are strikingly clear, and zeroing it out barely changes anything. It represents contraction avoidance without driving it. This is what I call the identity versus power distinction. A feature can clearly encode an interpretable concept without actually mattering to what the model produces. And if you don't run the causal test, you'll never know the difference. This isn't just us. Recent work by Enk Bayar found that only about 25% of highly active SAE features in a sentiment classification task encoded genuine task-relevant information. Our result, 2 out of 15, about 13%, is in the same range. Lee and colleagues showed separately that SAE concept representations are fragile enough that small input perturbations can manipulate them without affecting the model's actual behavior. These are what might be called interpretability illusions, convincing feature interpretations that don't survive causal testing. That was layer 22, the model's late-stage processing. We ran the same analysis at layer 16, which had 6 LoRa-specific features, and the result was different. 3 of the 6 showed causal signal. A 50% hit rate compared to 13% at layer 22. And one of them, feature 9868, is the second largest single token effect we measured across either layer. Feature 9868 fires on 30% of all evaluation data, Its top affected tokens are retire, peace, freedom, heart, unconquered. That's the vocabulary of Stoic inner retreat, Marcus's recurring theme of withdrawing into one's own rational nature. At layer 16, we also found features encoding ethical action and moral obligation. What emerged was a depth-organized encoding. Layer 16 handles what I'd call the practice of Stoic philosophy, retreat and action. Layer 22 handles the principles, virtue, and method. Concrete to abstract, stacked by depth, which is exactly what we'd expect from transformers based on prior work. But this also explains why most of the dedicated features are decorative. A LoRa adapter is a low-rank update. It gets a handful of independent directions to work with. The most parameter-efficient strategy isn't to build 15 new circuits. It's to take the hundreds of features the model already has and adjust their relative volumes. The dedicated features the SAE finds are largely byproducts of that process. They're representational echoes, not functional circuits. The real work happens through a distributed reweighting of shared features. Which brings us to the number that really tells the story. 78% of modern commentary chunks fire 0 LoRa-specific features at layer 22. Not one of the 15 dedicated features activates on these chunks. Yet those 0-featured chunks still show a mean reconstruction gap of nearly 5 times. The model is changed substantially for this text, and the LoRa-specific features have nothing to do with it. Where does the signal live? In the shared features. The LoRa reweights features that both models use, turning some up and others down. About 35% of the variance and reconstruction gap is explained by the LoRa-specific features. The other 65% is attributable to shared feature reweighting. And here's the wall. We tried to read those shared features through Logit Lens, projecting them into vocabulary space. The results were gibberish. Unlike the dedicated features, which pointed to recognizable words, the shared features map to incoherent token fragments. The mechanism that does most of the work is the mechanism that resists interpretation. We couldn't read the shared features individually, but we could ask what text they fire on, and that gave us something. We looked at all 271 shared features and asked, which ones get turned up by the fine-tuning, and which ones get turned down? Then we cross-tabulated that with whether each feature fires preferentially on archaic or modern text. The result was striking. Suppression, turning features down, is the majority outcome for every group. 70% of archaic dominant features get suppressed, 64% of mixed features, 82% of modern dominant features. The fine-tuning doesn't selectively boost archaic features, it suppresses everything. But it suppresses modern dominant features the hardest. The archaic style emerges from differential suppression. The model turns down all shared features, but turns down the modern ones the most. What's left, the residual after the broad suppression, tilts archaic. The LoRa isn't amplifying Marcus's world. It's clearing away everything that isn't Marcus, and what survives is him. There's one more piece. Within the archaic chunks, all written in the same register, all drawn from the same translations, the reconstruction gap still varies about 10 to 1. What distinguishes the passages the model changed the most from the ones it changed the least? The high gap vocabulary is distinctively Stoic and cosmological. Universe, which appears in 16% of high gap passages and 0% of low gap. Nature, death, reputation, remembered. The low gap vocabulary is generically philosophical. Thoughts, simple, divine, words that could appear in any philosophical tradition. The model changes most for content that is most specific to Marcus Aurelius: cosmic order, mortality, the worthlessness of fame. It changes least for philosophy that could belong to anyone. This is the same mechanism we found in differential suppression, now visible at a different resolution. At the feature level, the model suppresses generic features and lets distinctive ones survive. At the vocabulary level, passages with distinctive Stoic content show the largest internal changes. Two independent measurements converge on the same mechanism. The model sculpts by selective removal, and what survives is what's most specific to Marcus. 3 takeaways, in order of how uncomfortable they should be. First, finding features is the easy part. We found clean, interpretable features. They're real. They activate on the right inputs. And at layer 22, 13 out of 15 don't matter. Layer 16 was better, 3 out of 6, but even there, half were noise. Activation patching is not optional. Without it, you're reading the model's notes, not its work. Second, the mechanism that matters resists the tools. 65% of the signal lives in shared feature reweighting, distributed across hundreds of small adjustments to features that individually look unremarkable. The metaphor of finding the feature for X breaks down when the real mechanism is a coordinated shift in hundreds of features that each encode something too tangled to name. Third, all of this operates at the token level. Every measurement in this study is computed one word at a time. If the fine-tuning taught the model to track the flow of a Stoic argument across a passage, or to sustain a mode of philosophical reasoning over multiple sentences, our tools cannot see it. The token-level results give a lower bound on the philosophical signal, not the full picture. The differential suppression finding offers a partial consolation. Even though we can't read the individual shared features, the aggregate pattern is clear: broad suppression with a modern dominant gradient. The model sculpts by removal. That's a genuine mechanistic insight, even if we can't yet break it into individually interpretable pieces. The question for the field is whether this is a general mechanism or specific to our case. Does fine-tuning always work primarily through distributed reweighting rather than dedicated feature construction? Other domains, code style, dialect shifting, technical jargon, could test that. We think it's general, but that's a hypothesis, not yet a finding. If you want to dig into the numbers, the full write-up with charts and key statistics is on our Substack. This work was a collaboration with John Holman. I'm Arshavir Blackwell, and this has been Inside the Black Box.